First, let's talk about statistical inference. So remember, we said statistical inference was using sample data to draw conclusions about the entire population. And we basically have two different methods for statistical inference. The first one is called a confidence interval. And the purpose of a confidence interval is to estimate the value of a parameter. Okay, and from last time, who remembers what a parameter is? Okay, so a parameter is a number that describes the population. The purpose of a confidence interval then is to estimate that number that describes the population. So typically we're talking about things like the population mean, the population proportion, the population correlation. We could be talking about the difference in two population means or the difference in two population proportions. Those are the main things we're going to look at. The other method for statistical inference is called a hypothesis test. And the purpose of a hypothesis test is to assess the evidence for a claim about the population. All right, so kind of to highlight the differences between when we would use these two methods, let's say I am interested in Pizza Hut delivery times. So I just want to know, hey, what is the mean Pizza Hut pizza delivery time? So if I just want to know what is the value of my parameter, then I would do a confidence interval. So a confidence interval, in the end, we're going to find out today that it's going to give me a range of values where I'm pretty sure the population parameter is. So I can have a good estimate of that population parameter. Now, on the other hand, if you're old like me, then you probably remember those commercials that Pizza Hut used to do where they used to say, hey, we deliver your pizza in 30 minutes or less. And maybe you're thinking, I'm not sure if they really do deliver their pizzas in 30 minutes or less. That's a pretty bold claim there. So you want to collect some data to test that claim, to see if it's actually true. Do they really deliver their pizzas in 30 minutes or less? So in a hypothesis test, we're going to collect some data, and then we're going to use the information in the sample data, and compare that to the claim. And if they're close, then we're going to be like, okay, I guess I can't say they're wrong. And if they're really far apart, they're going to be like, gotcha, Pizza Hut, you do not deliver your pizzas in 30 minutes or less, kind of thing. So that's kind of the difference there. It's just what your end goal is, whether or not you're going to do a confidence interval or a hypothesis test. And we are going to focus all about confidence intervals here in chapter 3 for the remaining 3 sections of chapter 3. And then in chapter 4, it's all focused on hypothesis tests. So we're going to learn a lot about those. And like I said, confidence intervals and hypothesis tests, this is what we're doing from now until the end of the semester. So if you can kind of latch on to the principles in these next couple of chapters and really understand what a confidence interval is and how to interpret a confidence interval and how to do a hypothesis test and how to draw conclusions, those things are going to help you for the rest of the semester, because we're just going to keep doing more confidence intervals, more hypothesis tests, but we're going to mix things up a little bit as we progress through the chapters for the rest of the semester. Okay, so there was a random sample of 1,483 adults in the US that were asked whether they consider a car a necessity or a luxury. And 86% of the sample said that they considered it a necessity. So our population here would be all adults in the US. Our sample is these 1,483 adults that we actually talked to. And we know that our sample value is 86%. So p hat is going to be 86%. But how accurate is that 86%? Because we also know that if we were to take another sample, that we probably wouldn't get the same exact answer. We probably wouldn't get 86%. And we know that 86% is probably not exactly equal to the population value. So we know that it's probably not equal to the population value exactly. We know that if we took another sample, we'd get a different value. So how can we use this 86% to draw some kind of conclusion about the population? The 86%, we call that a point estimate. So we mentioned that term last time, point estimate, and we said it's the same as the sample statistic. So the sample statistic is going to be our point estimate. And by point estimate, we mean a single value estimate for the parameter. but relying on this idea that, hey, we're pretty sure that's not the exact value, then what would be better is if we could give a range of values where we're pretty sure the population parameter is. And that's what a confidence interval is. A confidence interval is going to give us a range of values that say, hey, we're pretty sure that the actual parameter is in this interval. Let's write some of that stuff down. So we're going to kind of define confidence interval and some other terms that go along with confidence interval. So first term then is confidence interval. So this is kind of the technical definition for confidence interval. We already said that the purpose of a confidence interval was to estimate the value of a parameter. So a confidence interval, when we define it, is going to be an interval computed from sample data by a method that will capture the parameter for a specified proportion of all samples. All right, so again, it's going to be like this interval where we're pretty sure that the population value is, and it's going to be based on a method that we're going to be able to know how correct that method is, basically. So that's when it's talking about this specified proportion of all samples. Well, using this method that we're going to use, we're going to know what percent of the time we're going to be correct, basically. So the confidence level, next term, the confidence level is going to be our success rate. So it's the proportion of all intervals or all samples whose intervals contain the parameter. All right, so let's talk about the basic format of a confidence interval. So the basic format of a confidence interval is we're going to have our sample statistic, that point estimate, plus or minus what we call a margin of error. And probably not all this lingo is new to you. You've probably heard about margin of error before, or maybe even seen something. A lot of times when they publish studies, down below at the bottom, it'll say like the margin of error for this study is plus or minus 3% or something like that. And they're helping you come up with this interval estimate when they do that. So margin of error, sometimes we code it ME, so we use like an acronym to talk about margin of error, is basically just a number that reflects the precision of the sample statistic as a estimate for a particular parameter. So it's a number that reflects the precision of the sample statistic as an estimate for a particular parameter. All right, and probably how you'll think of it most of the time is, oh, the margin of error is the thing that we just add and subtract from the sample statistic to get our confidence interval. And that's basically what it is. We'll talk more in a minute about how to come up with the margin of error. We're talking about this study that they did with the 1,483 adults, and they were asked whether they considered the car a necessity. 86% of the sample said they considered it a necessity, and later on in the report it says the maximum margin of sampling error is plus or minus 3 percentage points. So now that they've given us the margin of error, then we can go ahead and compute a confidence interval. So we're going to take that 86%, we're going to add and subtract the 3%. So 86 minus 3 is 83, 86 plus 3 is 89, and we typically write the lower and upper bounds of our confidence interval in parentheses like this. So we have parentheses, lower bound, comma, upper bound, and parentheses, just like this. And this is where we're pretty sure that the actual proportion of everybody, if we were to ask everybody, all adults in the United States, whether or not they considered a car a necessity, we think it would be, or we're pretty sure that it's somewhere between 83% and 89%. Okay, that's the basics of what we're talking about with our confidence interval here. So let's look at another example here. So here's a random sample of 30 salaries for Major League Baseball players. And in that sample, the sample mean was 4.55 million, and it had a margin of error of 1.98 million. Okay, so my population would be all Major League Baseball players. My sample is these 30 Major League Baseball players that I've actually found the salaries for. And the value for my sample, X bar, is this 4.55 million. And we also know that the margin of error is 1.98 million. So see if you can create an interval estimate, so a confidence interval for the mean salary for all Major League Baseball players. So take a second to do that on your paper, and then we'll see if we all got the same answer. All right, so what kind of numbers did you get for your interval estimate, for your confidence interval? We take that 4.55, we subtract 1.98, that gives us the 2.57. Then separately, we take 4.55 plus 1.98, and that gives us 6.53. So we're saying, hey, we're pretty sure that the mean salary for all Major League Baseball players is somewhere between 2.57 million and 6.53 million. All right, so last time we looked at some of that polling data from the 2016 presidential election, and this is a couple of the values that came from those polls that we were looking at last time. So here's two different polls, the Quinnipiac poll and the Monmouth poll. And you can see here it gives their point estimate for the proportion of people who said they plan to vote for Clinton. And in this column here where it says MOE, that stands for margin of error. So for the Quinnipiac poll, it was 3.1, and for the Monmouth poll, it was 3.6. So why do these two confidence intervals have different margin of errors? Based on the information that they're giving us right here, why would the Quinnipiac poll have a smaller margin of error than the Monmouth poll? Yeah, great. It has to do with our sample size. So if we look, we can see the Quinnipiac poll sampled 1,007 likely voters, whereas the Monmouth poll only sampled 726 likely voters. And remember how we talked about the variation of that sampling distribution, right? So there's less variation in the sampling distribution as the sample size increases. So that's going to be reflected in our margin of error. So if we have a bigger sample size, that's going to give us a smaller margin of error because we're going to be able to estimate the parameter value more precisely. Okay, so using the Quinnipiac poll here, let's see if we can calculate the confidence interval for the proportion of likely voters who plan to vote for Clinton. So we can see that the point estimate was 50 and margin of error is 3.1. So what would be an interval estimate for the proportion of likely voters who plan to vote for Clinton? Yeah, 46.9 to 53.1 is our interval. So we're saying, hey, we're pretty sure that the proportion of all voters who plan to vote for Clinton is between 46.9 and 53.1%. So when we have this confidence interval, basically all the values that are in our confidence intervals we would consider plausible values for the population parameter. And any values that are not inside the confidence interval, we're going to say those are not plausible values for the parameter. So based on this interval, we're saying anything between 46.9 and 53.1 is a plausible value for the true population parameter. Now with elections, one thing that's kind of interesting about them is that we can take these polls and if we're pretty close to the election day, which these were just within a couple weeks of the election date, these polls that were done. And when we take our poll, we're only taking a sample, but then on election day, we get the real population value. We actually see what percent of the voters voted for each candidate. And if we look at the actual election in 2016, we could see that Clinton received 48.2% of the votes. So did our interval estimate contain 48.2? Did it have the true value for people that voted for Clinton in it? Yeah, went from 46.9 to 53.1. 48.2 is in that interval. So our interval did capture the true proportion of people who voted for Clinton. Okay, so let's talk a little bit more about margin of error and where margin of error comes from. So margin of error, we've already noticed that when our sample size gets bigger, then our margin of error gets smaller. And it basically all comes back to the variability of the sample statistic. So the margin of error is going to be based on the variability of the sample statistic. And the name for the variability of the sample statistic is the margin or the standard error. So essentially, margin of error is going to be based on standard error. So if we can estimate the standard error, then we can use that to construct a confidence interval. All right, so let's talk about how we can do that and kind of the logic behind how we're going to come up with our method for constructing these confidence intervals. So this is a sampling distribution, and it's a sampling distribution for a mean. I actually don't know what data that this came from, so I won't tell you the backstory on it. It's a sampling distribution, so I know that one dot on this sampling distribution represents one sample mean, right? And I can see the center of this sampling distribution is about 43.2, so that means that my population parameter value is somewhere close to 43.2, because I know that my sampling distribution is centered on the population value. So each of these dots represents a sample mean that I could get by taking a sample from this population. And this one's based on 2,000 samples, so this gives a pretty good representation of the different types of sample means we could get taking a sample from this population. And if we look at values for sample means like 40 or 35, does it seem likely or unlikely that you would get a sample mean that is, say, 37? Does 37 seem like a likely or unlikely sample mean to get from this population? Yeah, likely, okay, likely because look, there's a whole bunch of sample means that were 37 or really close to 37, so it's a pretty likely value. What about 25? Is 25 a likely value for a sample mean? Okay, so this one's a little bit more unlikely. There's not as many values that are out here by 25, so it's more unlikely, but it's not impossible, right? There were some sample means that we saw when we took all these random samples that had sample means that were around 25. So it's unlikely, but still possible. And what about a sample mean of like 10? 10 is like super duper unlikely, right? When we took 2,000 samples, we didn't get any sample means that were anywhere close to 10. So it seems almost impossible to get a sample mean of 10 or less based on our sampling distribution here. Okay, so now let's think about some things that we know about distributions like this. So this is a bell-shaped symmetric distribution, and if you recall, according to the 95% rule, then 95% of values are going to be within 2 standard deviations of the mean. So in this case, the mean of our sampling distribution is the parameter value, and the standard deviation of our sampling distribution is the standard error. So we're basically saying, in this case, that 95% of sample means, because that's what these little dots are, will be within 2 standard errors of the population value. So 95% of sample means will be within 2 standard error values of the actual population value. So, but when I say like within, that means like if I take my sample value and I add and subtract 2 times the standard error, then that interval should capture the population parameter value for 95% of all sample means. So that's the method that we're going to use to construct our confidence interval. So it's based on this idea here, okay? So, and this graph kind of shows me, hey, if I get any of these sample means that's black, one of these black dots, and I add and subtract 2 times the standard error, so my standard error is about 9 in this case, 2 times the standard error would give me about 18. So whatever sample mean I get, if I add and subtract 18, 95% of the time, my interval is going to have 43.2 inside of it. All right, so 95% of the intervals created with this method will contain the true value of the parameter. So if 95% of the time my intervals contain the true value of the parameter, then what happens the other 5% of the time? It doesn't contain it. So this interval is not going to be 100% foolproof. we're going to be right 95% of the time, which is a pretty high percentage of the time to be right. I mean, if you could be right 95% of the time, all the time, wouldn't that be amazing? Like if you're right on, 95% of your test questions, or if you were right in 95% of your arguments with your significant other, or anything like that, like being right 95% of the time would be super fantastic, right? And again, looking at my picture here, all these black dots, when we create an interval for those using this method, we're going to get an interval that contains the true value. Now, there's going to be 5% of those dots. Those are all these little unlucky red ones over here, where if I happen to get one of those sample means, when I create my interval and I add and subtract that 2 times the standard error, it's not going to have the true population value in it. So my interval is going to miss it, and that would be sad. And in real life, we're only going to take one sample, so we're not really sure which of these dots that we're going to get. But looking at this, is it more likely that I'm going to get a black dot or a red dot? It's a much higher probability that I'm going to get a black dot, right? Like if you're kind of reaching your hand into the bowl of dots here, like you're probably going to get a black dot. So we can be pretty confident, that's where the word confidence comes in, right? That our interval contains the true value of the parameter, because 95% of the time it's going to. And if we happen to be one of these unlucky little red ones, we won't know it because we only took one sample and we don't actually know what the population value is. So it will be sad, but it's not going to happen that often, only 5% of the time. Okay, so this is the method that we're going to use then to construct our confidence interval. And we're going to call it a 95% confidence interval, because if you remember when we talked back about the confidence level, we said it's our success rate. And using this method, we're going to have a success rate of 95%. We're going to get an interval that contains the true value of the parameter 95% of the time. So to do that, we're going to take our statistic plus and minus 2 times the standard error. So one thing that sometimes students get a little bit confused about is, we already gave the basic format for the confidence interval. It was very, very similar to this. And basically the difference was that instead of having 2 times the standard error, the last one that we wrote down just said margin of error. So margin of error and standard error are different from each other. So pay close attention to the wording in the problem and see if it's giving you standard error or margin of error. But we can use the standard error to get the margin of error. So 2 times the standard error is equal to the margin of error. So as long as you just look and see which one you can get to the margin of error. You can add and subtract that from the statistic, and then you have your confidence interval. Let's look at an example here. A survey of 1,502 Americans in January 2012 found that 86% consider the economy a top priority for the president and Congress. The standard error for this statistic is 0.01. What is the 95% confidence interval for the true proportion of all Americans that considered the economy a top priority at that time? All right, good. So the key word to watch out for here is they gave us standard error and told us that it was 0.01. So when I'm calculating my confidence interval, if I have standard error, first I have to multiply it by 2 to get my margin of error, and then I'm going to add and subtract that to get my confidence interval. So my statistic was that 0.86. I take 2 times the 0.01 to get my margin of error, add and subtract that, and I get 0.84 to 0.88. Okay, here's another one. In a random sample of Quebecers, 28% thought that Quebec should secede from Canada. If we use that sample statistic to estimate the true proportion of Quebecers who think that Quebec should secede, the margin of error is 4%. So what would a 95% confidence interval for the true proportion be? All right, we're getting a couple mixed answers over there. Now I'm getting a lot more D's out of there. D is the correct answer. So in this case, Then they did tell us that our margin of error is 4%. So this time they gave us margin of error. When they give us margin of error, we don't have to do anything. We've already got the margin of error. So we're going to add and subtract that from our sample statistic, which in this case was that 28%. So I would take 0.28 plus or minus 0.04, and that gives me the 0.24 to the 0.32. Or you could take 28% plus or minus 4%, and you would get 24% to 32%. So a bunch of people put B, but why would I mark B wrong on a test if you put B? What's wrong with B? Or maybe I should say, what is B missing that makes it incorrect? Yeah, when we talk about proportions, then we can't straddle the fence. We have to be on one side or the other. So either you have to report it as a proportion, a decimal number, or you have to report it as a percent with the percent sign. So if you don't have the percent sign, then I'm like, oh, I have no idea if they know what they're talking about. So I would mark it wrong. So if you were this would be correct if it had, I don't know if I can draw it on the computer, I'll try. If it had percent signs by it. Those are super ugly percent signs. I don't have my computer pen now, I'm just doing it with the mouse today. Okay, so if they had percent signs by it, then it would be correct. But because it's missing the percent sign, that makes it incorrect. So just be very careful with the way that you report things, especially when you're going back and forth between decimal and percent. Okay, next question. So remember your interval from the last one. So I'll go back up there. So the interval went from 0.24 to 0.32. So keeping that in mind, how many of the following are plausible values for the true proportion? Okay, so our interval went from 0.24 to 0.32. Everything inside that interval is going to be considered a plausible value, and everything outside the interval, not a plausible value. So 22, not in the interval, not plausible. 28, hey, that one's in the interval, so plausible. 30, that one's in there, plausible. 35, not in there, not plausible. 40, or 40%, 0.40, not in the interval, not plausible. So yes, C is the correct answer for that one. All right. Let's talk a little bit now about what the confidence interval means, kind of what it's doing, and how we're going to interpret the confidence interval. And then we're going to have a little practice with that. So confidence intervals, and this little graphic is going to help us here. Some key things to remember are, first of all, that the parameter is a fixed value. So parameters are fixed. That means that they don't change, and it's just a single value. So a parameter is a single fixed value. If we could somehow measure everybody in the population, we would be able to compute this single fixed value from everybody in the population. We typically can't measure everybody, so we're just trying to guess at what that single fixed value is. So in my graphic over here that I'm going to kind of explain, this black line that goes right down the middle represents my parameter. Okay, it is a single fixed value. And down at the bottom here, you can see it's equal to 50. I don't know what they're measuring on this one either. Okay, but the parameter value is 50. Okay, and it looks like they're doing means, so mu was equal to 50. All right, the statistic, when we take a sample and we compute the sample statistic, is random because it depends on the sample. And if we take another random sample, then we're going to get a different value for the statistic. So remember, the statistic is calculated just from our sample data. So statistics are random, they depend on the sample. And because of that, because we're creating our interval using the sample statistic, then our interval is also random. Okay, we're taking a sample, we don't know exactly which sample statistic we're going to get, which interval we're going to end up with, because it all depends on our random sample. So sample values and intervals vary from sample to sample. Parameter value is fixed. So looking at my picture over here, what I have is a whole bunch of different samples, and each one of these little lines represents the confidence interval that was computed based on that sample statistic. So the little white dot in the middle of the line, that would be my sample statistic, and then the lines that extend on either side, that represents the kind of the width of my confidence interval. So when that interval has the black line in it, then it's green, because that means that that interval contained the true value of the parameter. And when my line, which represents my interval here, does not have that middle black line in it, that's when it's red, meaning that it did not capture the true value of the parameter. It was too high or too low. So looking here, there was 100 intervals that were done here. And out of those 100 intervals, 95% of those intervals were green. They contained the true value of the parameter. 5% of those intervals were red. They did not contain the true value of the parameter. So again, this is showing us that, hey, if I'm doing a 95% confidence interval, what that means is that 95% of the time, my interval is going to contain the true value. So if I was to do this lots and lots of time, 95% of all 95% confidence intervals will capture the truth, will capture the true population parameter, which in this case is that black line. So the bubbles in the middle are the sample statistic. So we take our sample statistic and then we add and subtract that margin of error. So that's the two lines on either side represent the margin of error. So if I look at just where that green is, that shows me the span of the confidence interval. Okay, so let's talk about then how we're going to interpret a confidence interval. And there's actually a lot of wrong ways to interpret a confidence interval, and a lot of wrong words that you can use that when you're just learning statistics and you don't really understand it fully yet, like students are totally tempted to throw some of these words in there because they might sound good, they might even sound statistical. So they throw these words in, but it actually makes it incorrect. So just like I did when we were interpreting the slope and I gave you a little bit of what am I saying? I gave you a little, like a pattern. I gave you a pattern to follow to write your interval, not your interval, to interpret the slope. So when we talked about slope, I gave you a little pattern to follow to write your interpretation of the slope. So now I'm going to do the same thing for the confidence interval, and I'm going to give you like a little pattern that you can follow to write your interpretation of the confidence interval. And I recommend that you use this pattern until you feel really confident in your ability to interpret confidence intervals. It's not the only way to write an interpretation for a confidence interval, but for right now, if you use it until you really understand what things are right and what things are wrong, then it will help you so you don't write the wrong thing, especially on a test or something. And I can't put the last screen in the comments because it wasn't something that I typed in. It was just on my PowerPoint slide. Sorry, Natalie, but I can go back at the end of if you want to hang out after class, I can go back and show you that slide. Okay, so this is kind of the basic pattern per se that we're going to use. Okay, so we are going to say we are, and then we're going to fill in the blank with whatever our confidence level is, which for today, we've only been talking about 95% confidence intervals. And next class, we're going to look at, okay, well, what if I want to be more confident than 95%? Or what if I want to be less confident than 95%? Can I create a confidence interval that's different from 95%? And the answer is yes, and we're going to talk about how to do that. For today, this is always going to be 95%. So we'd say we are, whatever your confidence level is, percent confident that the true, and then this is going to be your parameter written out in words. So we had an example like this in class last time where we defined the parameter in words. And basically whatever you write there, however you define your parameter in words, then you're going to plop those words right in here. And then you're just going to say is between, and you're going to have your lower limit value and your upper limit value. And if you want to go the extra mile, throw those units on there as well, and then that makes you look really cool. So that's it. It's kind of basic, but like I said, there are a few ways that people write a few things wrong in there. So we'll talk about that. But first, let's see if we can write a confidence interval conclusion for this example that we've been looking at. So we created this confidence interval for the percent of Americans that considered the economy a top priority. And we said it went from 0.84 to 0.88. Okay, so let's see if we can come up with a conclusion statement using that pattern about this confidence interval. So looking back up here, okay, start with we are, and ours was a 95% confidence interval. So I'd say we are 95% confident that the true, okay, now I want my parameter written out in words. So if I was going to define my parameter is the proportion of all Americans that considered the economy a top priority. So that's what I'm going to fill in the blank there. Yes, it's long, and you might feel like you're getting a hand cramp when you write out these interpretations, but it's got to be done. You don't want to shortcut it because you might get in trouble when you shortcut. So I'm going to say we're 95% confident that the true proportion of all Americans who consider the economy a top priority, and then I'll say is between, and I'm going to put 0.84 and 0.88, or you could write 84% and 88%. So here it is all written out for you. We're 95% confident that the true proportion of all Americans that consider the economy a top priority in January 2012 is between 0.84 and 0.88. And that's it. Okay, so let's talk about a few of the things that you have to be careful of when you're writing your interpretation. And a big one here is the use of this word confident. And let me go back up to this thing here. Okay, up here, I say we're whatever percent confident. You can also use the word sure. So I tend to always use the word confident because that's how I've done confidence intervals for the last like 20 years or 25 years, however long I've been doing statistics for. And most of the textbooks that I've used use the word confident, but this textbook that we're using right now likes to use the word sure. And sure is an okay word to use. So it's okay to use confident or sure here. Those are pretty much the only two words that you want to use there. So one word that people like to use, but it is incorrect, is they like to use the word chance or probability. They want to say, oh, there's a 95% chance that the true proportion is in this interval, or there's a 95% probability that the true proportion is in this interval, okay? But don't use words like chance or probability when we're interpreting a confidence interval. And you might be wondering why, because you're like, hey, I thought this was all based on probability. You told me if I use this method 95% of the time, I'm going to get a value in there. That sounds like probability to me. And you're right. The method is based on probabilities. It is. But probability can only be used to describe something that is in the future. So we can only use probability to talk about something that hasn't happened yet. When we take a sample and we compute our confidence interval, it's not something that's in the future, it already happened. Once we collect our sample, it's an event that's in the past. Once we collect our sample and we compute our confidence interval, either the population value is in there or it isn't. There's no probability, because the probability would have to be 0 or 1. But it would definitely not be 95% because there's nothing that's going to change. Remember, the parameter value fixed. Once I've computed my interval, then that interval is not going to change based on that one sample. So either parameter in there or parameter's not. Sometimes it helps if you think about it with relation to the weather. So if I'm talking about tomorrow's weather, then I could say, hey, there's a 40% chance that it's going to rain tomorrow. And that is an okay statement to make because tomorrow hasn't happened yet. So we're saying it could rain, it couldn't rain, there's a 40% chance. But if I'm talking about yesterday's weather, I can't say there's a 40% chance that it rained yesterday because yesterday's past. So either it rained or it didn't rain. There's no chance. There's no way that yesterday's weather is going to change because it already happened. So we can't use chance and probability to describe events that have already happened. And once we've computed our confidence interval, actually once we've collected the data, then the event happened, okay? And either the interval contains the value or it doesn't. So don't use chance or probability when you're writing your confidence interval statement. The other thing that you have to watch for is you have to remember what it is that our confidence interval is telling us. And our confidence interval is telling us that we expect our parameter value, our value from the population, to be in that interval. That's it. It just says we expect, you know, if we're talking about a mean, we expect the population mean to be in the interval. Or if we're talking about a proportion, we expect the population proportion to be in the interval. So here's some things that it doesn't tell us. It doesn't tell us where individual values are, okay? So it's not going to tell us where each person in the population value is expected to be. It's just telling us where the mean of all the people in the population is expected to be. Another thing it doesn't tell us is it doesn't tell us about sample means or future sample means. It's only telling us where the population parameter is expected to be. That's it. So, like I said, watch for some of those wording things because they come up and they can be tricky. When you're writing it out yourself, and you can follow that little pattern, you can usually just follow the pattern and you'll get it. But if I were to ask you questions on a test or like some questions on your written homework this week about whether or not it's a valid interpretation of a confidence interval, that's where some of these things are going to start to creep in. So you need to be able to read it and be like, wait a second, you know, they can't actually conclude that. That's not a valid conclusion. Or, yeah, that sounds good. That is a valid conclusion. Okay, so here's a few common misinterpretations. First one, a 95% confidence interval contains 95% of the data in the population. So the things that's wrong with this one is the of the data. Remember, the confidence interval doesn't tell us where individual data points will be. It just tells us where we expect the population value to be. Here's another common misconception or misinterpretation. I'm 95% sure that the mean of a sample will fall within a 95% confidence interval for the mean. So again, our confidence interval doesn't tell us about sample means. We're looking for it to tell us where the population mean is. And then I bet you can tell what's wrong with this last one because I've already been on my soapbox a lot about this one today already. So this misinterpretation, the probability that the population parameter is in this particular 95% confidence interval is 0.95. So again, once we've computed our interval, the probability is either 0 or 1. It can't be 0.95. It either happened or it didn't happen. It's either in there or it's not. Okay, so we are going to look at a couple of examples, kind of start to finish. A little bit of last time, like identifying the population and defining the parameter, and then we're going to take it one step further and compute our confidence interval and also write our interpretation for the confidence interval. Starting with this one. So this one says, in a nationwide survey of 1,484 people age 18 plus living in the continental US, 623 people said that a TV was a necessity. The standard error for this estimate is 0.015. So our first question is, what is the population of interest? So what do you think the population is? And sometimes it can help. When I think of the population, I like to think of the word all because it reminds me that population is big. It's like everybody in this group that I'm interested in. So So I see lots of good answers in the chat window. Adults living in the US, 18 plus in US, people 18 plus, all those are good. I'm gonna throw the word all in front of there because that's gonna remind me that I'm talking about everybody and not just the people that I sampled here. So I'm gonna say all US adults. Okay, so my population is all US adults. Next question is going to be, what is my sample? Who did I actually measure? Yeah, I measured those 1484 adults. So my sample was just those n equals 1,484 adults that were living there. You could write it as n equals, but I don't really care if you have the n equals there, as long as you know that the sample is these 1484 adults and not all adults. Okay, next question then. What is the population parameter that we are estimating? So when you're trying to figure this out, you can kind of think about that table that we created for the last exam. We got to figure out, okay, well, what were we measuring and how many and what type of variables did we have? So in this case, it looks like we're just asking these people whether or not they thought TV was a necessity. So we have one variable. The variable is whether or not they thought TV was a necessity. So what type of variable is that? Is that categorical or quantitative? Categorical. So I have one categorical variable. So if I'm dealing with one categorical variable, then I'm dealing with one proportion. So what is the population notation for one population proportion? P, exactly. Okay, so P, and then when I'm defining the parameter in the context of the problem, now I want to write out in words what P represents. Remember, I don't have a number for the population parameter because in order to have a number, I would have had to have measured everybody, which I rarely do. So in these types of examples here, I'm not going to have a number for the parameter. I'm going to write out in words what it means. So P is a proportion. So proportion is the first word that should follow the equal sign. And what is it the proportion of? Well, it's the proportion of all US adults. Okay, because remember the parameter came from is representing the population. So it's going to be the proportion of all US adults who think TV was a necessity or is a necessity. All right, so that's my parameter. So I've given the notation P and I've described exactly what it means in words. So P is the proportion of all US adults who think TV is a necessity. All right, so next we're going to look at the best estimate. And when I say what is the best estimate, what is best estimate code word for? Yeah, the sample statistic. So best estimate is the code word for sample statistic. So what this is really saying is, what's the sample statistic? So the sample statistic, first we need to come up with the notation, and then we're going to come up with the value, because we don't have a value for the parameter because we didn't measure everybody in the population, but we do have a value for the sample statistic because we did measure everybody in the sample by definition, right? So if my parameter was P, what is my statistic notation? So the notation for the population was P, then my sample is going to be P hat. Okay, so my sample's P hat, and I can come up with a value for P hat based on the information that they gave me here. So they didn't come straight out and tell me the value of P hat. I'm gonna have to do a little bit of calculation. But remember that a proportion is just a fraction that's been turned into a decimal. So if it's a fraction that's been turned into a decimal, what are my numerator and denominator to figure out what P hat is? Good, so I'm gonna have 623 over 1484. So figuring that out on my calculator here, then I get 0.4198113. Okay, in our class, always do at least 3 decimals unless you're told otherwise. So I did see on a few of the homework things, people just round. You're going to get in trouble if you round too much in this class, especially once we get into some of the later chapters. So carry out at least 3 decimals unless specified otherwise. So in this case, I had 0.4198, rounding to 3 decimals, that would make it 0.420. Okay, so p hat is equal to 0.42. Basically, that's my best estimate for the parameter. All right, now let's talk about a confidence interval here. So for my confidence interval, we want to give a 95% confidence interval for the proportion of US adults who think that TV is a necessity. So what did they give me in the problem that's going to help me come up with my confidence interval? Perfect. They gave me the standard error. So they gave me the standard error and they told me it's 0.015. So if I want to get from the standard error to the margin of error, then I'm going to have to multiply by 2. So I'm going to take, so I'll just write that down first, I guess, the statistic, and I'm doing plus or minus my margin of error, which in this case, I'm going to have the statistic plus and minus 2 times the standard error, because that's what they gave me. So in this case, my statistic was that 0.420, and I'm going to add and subtract 2 times the standard error, which they gave me as 0.015. So that's going to be, if I multiply that 0.015, I end up with 0.03. So when I when I add and subtract, then 0.42 minus 0.03 is going to be 0.39. And 0.42 plus 0.03 is going to be 0.45. All right, so this is my confidence interval, the 0.39 to the 0.45. All right, so the last step here then is going to be to interpret that confidence interval. So we're going to follow that pattern that we were talking about there. So we're going to say we are 95% confident that the true, and now I'm going to fill in. So remember when we defined the parameter and we said P equals this, I'm just going to take those exact words and plop them right in right here. So we're 95% confident that the true proportion of all US adults who think TV is a necessity. Okay, so that's just taking that exact thing that we wrote when we defined the proportion, the population parameter. We're putting all those words here, and then we're going to say is between, and we're going to put our lower and our upper bound. So is between 0.39 and 0.45. And that's it. That's how we're going to write our confidence interval conclusion. So for our next example here, this goes back to this old commercial here. So we're going to watch this commercial real quick. It's only a minute long.
Mr. Cow.
Yes?
How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop?
I don't know. I always end up biting. Ask Mr. Fox, for he's much cleverer than I.
Mr. Fox, how many licks does it take to get to the Tootsie Roll center of a Tootsie Pop?
Why don't you ask Mr. Turtle, for he's been around a lot longer than I. Me? I bite.
Mr. Turtle, how many licks does it take to get to the Tootsie Roll center of a Tootsie Pop?
I never made it without biting. Ask Mr. Owl, for he is the wisest of us all.
Mr. Owl, how many licks does it take to get to the Tootsie Roll center of a Tootsie Pop?
A good question. Let's find out. 1, 2, 3, 3.
If there's anything I can't stand, it's a smart owl.
How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? The world may never know.
All right, so I love that old commercial. It's even older than me though, so don't worry, it's not from back in my day, it's from back in before my day. But basically there was a researcher at Siena Heights University in Michigan, and they wanted to find out the answer to this question that's been around forever. about how many licks does it take to get to the center of a Tootsie Pop. So he recruited 92 volunteers and he gave them all a Tootsie Pop. And ironically, I was cleaning out like the little, like when my kids make their lunch, they have like a little bin with the treats and a little bin with fruit and a little bin with snacks and everything, so they can just kind of grab things and put it in. And I found a Tootsie Pop. There was only one Tootsie Pop in there. I was like, oh man, that is so perfect. So I have my Tootsie Pop here. I can try it out after class. So these 92 volunteers, they licked their Tootsie Pop till they got to the center, and he recorded how many licks it took to get there. And the mean for his sample was 356, with a standard error of that estimate being 19. Okay, so first question is, what's the population? So what's the entire group of interest? Who are we trying to draw conclusions about? All right, so who are we measuring on? We measured these 92 volunteers, but they're representative of the whole population, or trying to represent the whole population of, yeah, humans would be good, or Tootsie Pop consumers, all people who eat Tootsie Pops. I think those are all good ones. So I'd say that the population, I'm gonna call it all Tootsie Pop consumers. Okay, so my population is all Tootsie Pop consumers. What about my sample? What's the sample here? Okay, my sample is the subset of the population that I actually measure. So in this case, my sample is going to be the 92 volunteers. All right, so my sample is these 92 volunteers. Next, we're going to talk about our population parameter. So first of all, we want to come up with the symbol for the parameter. So again, I'm going to look at what did I measure here, how many variables did I measure, and what type were those variables. So all he did was measure the number of licks that it took to get to the center. So number of licks, that's one variable. And what kind of variable is that? Is that categorical or quantitative? It's quantitative, okay? So I have one quantitative variable. So if I'm looking at my chart and I go over for one quantitative variable, then the population parameter is mu. So mu is going to be my population parameter. So see if I can draw that. And now I want to define what mu is in the context of this problem. So because mu is a mean, the first thing that follows the equal sign should be mean. Or you can write average if you like the word average better. So mean or average. And then what is it the mean of? Well, it's the mean number of licks. So I'm going to say mean number of licks to get to the center of a Tootsie Pop for all Tootsie Pop consumers, right? So we're not just talking about the mean of our sample here. We're talking about if everybody who consumed Tootsie Pops licked and counted the number of licks, then this would be the mean number of licks for everybody to get to the center. So it's the mean number of licks to get to the center of a Tootsie Pop for all Tootsie Pop consumers. All right, next we want the statistic, the best estimate for the parameter. So if my parameter was mu, then what's the notation for my statistic? X bar, exactly. So remember, the statistic and the parameter, they go hand in hand. So if you know one, that automatically leads you directly to the other one. So if my parameter is mu, my statistic is always X bar. And they tell us in this case that X bar, we have a number. Remember, we're going to have a number for the statistic, and that's going to be equal to 356. So X bar equal to 356. Next, we're going to do a 95% confidence interval. So they give us the standard error. They tell us it's 19. So we can go ahead and construct our confidence interval by doing 356 plus or minus 2 times 19. I'm taking 2 times it because they gave me the standard error rather than the margin of error. So I'm going to end up taking 356 plus and minus 2 times 19. So that's going to be 356 plus and minus, so 2 times 19 is 38. 356 minus 38 is 318. And then 356 plus 38 is 394. So my confidence interval goes from 318 to 394. So now all I have to do is interpret that confidence interval using our little pattern that we have going on here. So we'd say we are 95% confident that the true, okay, and now whatever we defined our parameter to be, that's what were those words that we're filling in right here. So the true mean number of licks to get to the center of a Tootsie Pop for all Tootsie Pop consumers is between 318 and 394. So is between 318 and 394, and these were measured in licks, so you can add the units on there, makes it sound better. All right, so that's basically how we're going to construct our confidence intervals. Okay, so if I want to create a 95% confidence interval, then I can take lots and lots of samples from the population, compute the sample statistic for each of those samples, and use that to create my sampling distribution. I could take the standard error, which is the standard deviation of that sampling distribution, to get my standard error, and then all I have to do is take the statistic plus or minus 2 times the standard error to get my confidence interval, which sounds so easy, except one small problem. Can anybody think about what the problem is? So this method requires me to take many random samples from the population. So in real life, we don't take lots and lots of samples. We only take one sample. So what are we going to do when we only have one sample? And that's the cliffhanger that I'm going to leave you on for the weekend. So on Tuesday when we come to class, we're going to solve this problem, and we're going to tell you what we're going to do when we only have one sample.